theory. This is okay. Good. So what I wanted to talk today is about, of course, dark matter, because one of the this is one of the most popular topic, popular direction in particle physics, because actually we don't know what is the particle physics. Sorry, because we don't know what dark matter is. That's very interesting. So, by the way, you're very welcome to interrupt me at any point. So it's I don't want my talk to be very formal. So I really would like to make sure that you are well, you can follow it, and if you uh, want to interrupt me, you are very welcome. Okay. So talking about the popular directions in particle physics. And this is just counting of number of papers from Spires, from Inspire. Used to be Spires, which is actually much better naming than Inspire. Well, quite unique. And dark matter, you can see that dark matter is the most popular topic, even above the Higgs and SUSY and TOP and extra dimensions. And this is the technicolor and dynamical symmetry breaking number of papers. So you can see that dark matter is by far leading one. And it's quite amazing that dark matter, though it's leading one, if you think about, well, the evidences for dark matter, of course, it's there, but we don't know what it is. We know that there is a neutral, heavy, stable particle there, which explains the galactic rotation curves, very precise CMB peaks fitting. Nowadays, well, the shift of these peaks, even by per mil precision, will be visible, and this is a very important thing. So the bullet cluster, large-scale structures, and gravitational lensing, well, are all independent confirmation of the existence of dark matter. Well, and what's interesting is that though there is a very strong evidence for dark matter, we have no idea about their properties. You can see that among all question marks, only one thing we know about dark matter. It interacts gravitation. There's no information about spin, mass, the symmetry behind its stability, and whether it's stable, quasi-stable on galactic, well, on the scale of the lifetime of the universe, whether it's thermal relic or not, and which interactions it involves besides gravity. Well, and on the way of kind of trying to answering this question, we need to, well, build as many theories as we need, as we want, and explore different properties of the theories. And this is quite amazing plot from my point of view, because if you think about dark matter mass, which spans from over 50 orders of magnitude, and strength of the interaction, which also spans over more than actually 60 orders of magnitude. And there is only a little bit which called WIMP. This is a little quadrant, and where the weakly interacting massive particles takes place. And there are many different models besides WIMPs. And I'm not going to talk about all these models because I don't have time and I don't want to be boring, because it's actually a separate, set of lectures devoted to all these models, to each of them. So, but it's interesting. I just want to zoom a little bit, if it's possible. Yeah, it's possible. So I just want to zoom and move a little bit towards WIMP. Yeah. So there are, yeah. Sorry for quality, because, well, I zoomed it a lot, but I just want to see there are two curves. One is the red one, which is related to direct dark matter detection exclusion, and one is blue, which is related to LHC. And you can see how complementary they are. because LHC excludes everything if it can produce. So everything above the blue line is excluded, and you can see that LHC is sensitive to lighter dark matter particle, while direct detection experiment are sensitive to the heavier dark matter particle, but of course they're limited by strength of interactions. And this is nice complementarity of LHC, which is blue curve, and direct detection experiments with the leading xenon and tone already, but it's there. So that's, I just want to kind of highlight. Okay, so I'm back to the standard zooming and just want to kind of talk about the theory space. Okay, the theory space of dark matter is, well, you can draw zillions of plots, of course. And the one I like, which actually the one of the first plot sketch of Tim Tate. Nowadays, there are many, many different sketches. And the one which I like the most is this one. Why? Because it shows the direction of complexity of the models, and there is the effective field theory models based on the effective field theory, which is involve only like one or two parameters. And then you go to simplifying models with the kind of few more parameters, and then you end up with the UV complete models, MSSM, with the, well, in general, 100 parameters. What I wanted to stress that here, well, in about 2 years ago, we have added one more piece which was missing, is the piece which we call minimal consistent dark matter models. These models are renormalizable, well, anomaly free, and actually each model from this kind of class can be independent model, contrary to simplified models, which very often maybe not even unitary sometimes. Well, when people introduce some Z primes or vector dark matter model or whatever. So, and classification of minimal consistent models was based on the following kind of criteria. So we consider the spin of dark matter, which was either 0, 1/2, or 1. This is spin of dark matter multiplet, because in general, we consider dark matter multiplet shown by a letter X, and it has tilde means odd particle or symmetry, which stabilize dark matter, and I means either spin and Y means hypercharge. And the minimal consistent dark matter models also include at most one multiplet of mediator. So vertical the vertical column indicates the spin of the mediator multiplet, and therefore the complete model is characterized by just two letters. One is dark matter, and another dark matter in another mediator multiplet. So there are two letters. So, but I'm not going to discuss much about this. Well, just to mention that MSSM is SUSY is here, and MSSM, including MSSM. This is, say, for example, spin half dark matter with the different mediators. But in general, this is the complete picture of the weakly interacting minimal consistent dark matter models. Well, we need to go further and actually consider something beyond weak interactions. And because if we like to make a complete classification of dark matter, the weak interactions are not the only one we should consider. So, and also would like to mention that the vector dark matter is the least dark matter explored. So we decided to go beyond weak interactions and explore properties of the vector dark matter. And in particular, the minimal the gauge symmetry as SU2 for vector dark matter. So what has been done previously, the dark matter was explored in vector dark matter was explored in connection to U1 dark group, the abelian group, with the Higgs portal. I mean, and there is a Higgs portal between the Higgs of standard model and the new Higgs, which actually breaks the U1 symmetry. And this is good, but in general, well, there is also non-abelian, well, dark matter with the Higgs portal. This is good, but and there is quite a few papers, but there are quite limitations for the Higgs portal. That's why I mean, we wanted to go to more general setup. What is the problem with the Higgs portal? The problem is the following. So first of all, I'd like to notice that the direct detection tells us that we don't see dark matter from direct detection point of view. That's why the coupling of the Higgs VV, because the Higgs portal means that the Higgs boson interacts with the vector dark matter, and the coupling of these interactions lambda HVV. So the non-observation of dark matter from direct detection experiments tells us that this coupling should be less than something, and this is this curve. So the blue curve is the curve excluded by xenon, and we need to be below this curve. I hope you can see my pointer, right? I don't know if you can see this. Well, can you?
Yes, we can see.
Good, good, good. So you need to be below this curve, and so coupling should be less than something. There is an upper limit on this coupling. On the other hand, we know that relic density is there. So relic density with the measured by Planck tells us that the relic density, which is equal to omega h squared, is of the order of 0.1 or below, tells us that the coupling should be larger than something. So, well, and this is the red line, the describing the thing. So the red line, you need to be above the red line or this purple line, whatever, above. So there's a lower limit on how small this coupling should be. And the only region which is survived in this kind of simple model is when you stay on the resonant. And even that, now the xenon 1 tone, excluding it even more, like somewhere here, and actually it can exclude quite seriously, in maybe even completely, this narrow tip with the Higgs resonance. That's the deep related to the region where dark matter annihilates through the Higgs resonance. So dark matter mass is 62.5 GeV. Well, and of course, if the coupling is too large, then you exclude it by perturbativity, but this is fine. And there's Higgs to invisible gray color, so you need to be actually below the gray line, but it's not very relevant because in direct detection excludes more. They superseded the Higgs invisible decay. Anyways, so one should think about the new mechanism of dark matter communication to the standard model sector. So, and that's the main reason why we actually managed to, well, we've been interested in vector dark matter with the fermionic portal. So there are three main ingredients of this construction. It's actually a very simple model, very simple class of models, I would say, or framework. So first of all, it's SU2 dark gauge group involved. And SU2 dark gauge triplets is related to vector dark matter. Second ingredient is the complex scalar doublet, which we call phi D. Well, you need to break the SU2 dark, and the exact analogy to standard model. So you need to have a scalar doublet here. And the last component and very crucial component of this construction is the vector-like fermion doublet. So the vector-like fermion doublet psi is the doublet with respect to SU2 dark group. And this is the guy who actually talks to standard model. And I will show how. So first of all, well, not first of all, but the next step is to assign dark charge to the component of the doublet. So we define the dark charge in exact analogy to the electromagnetic charge as Q dark is equal to the sum of the two components, the third component of the isospin, dark isospin, and dark hypercharge. Okay, so we require that this dark charge is conserved. And well, when SU2 dark breaks, well, the SU2 dark breaks to U1 dark global. So, well, after the symmetry breaking, well, with the dark Higgs. So once you require the dark charge conserved, well, there is a symmetry which defines the oddness or evenness of the particle as -1 to the power of Q dark, and this is group. This is the U1 global. For this U1 global, the Z2 is subgroup of that group. Well, and requirement of the conservation of the dark charge eliminates one of two terms which you can write. So besides these three ingredients, I mean, how would standard model talk? How does dark sector talk to standard model? You can write the following term. This is Yukawa interaction. So the psi, phi, this is doublet. So psi L is a doublet, phi D is a doublet, and then you need to write singlet. And the only thing you can write here is the singlet of standard model Fermionic here. So it's doublet, doublet, singlet. There are two ways you can write this Yukawa interaction. You can write where phi and phi conjugated. However, if you require dark charge is conserved, one or two of two terms will be forbidden. So if we choose yd equal plus 1/2, then actually this term will be forbidden because the conjugated term will violate the dark charge conservation. So if you choose yd equal -1/2, then this term will be forbidden. For concreteness, we choose yd equal plus 1/2, and then only this term is allowed. And this is the key point of the model. If you have any questions till this point, please let me know, because this is a really important thing. Any questions so far? So once the dark charge is conserved, dark matter is stable, because if you look at the stable and look at the dark charge assignment for the phi doublet. So again, here on the left, I'm just repeating what I said. This is nothing new. Well, but this on the right, this is the pictorial table which show the assignment of the quantum numbers. So the phi d is the scalar doublet, and the upper component has a +1 dark charge, and the lower component of this doublet has 0 dark charge. That's why if we think about that, where the wave goes, the wave should go to the lower component of this, should be at the lower component of this doublet, because the wave should not have any charge. And also this means that the upper component of this doublet, there are 2 degrees of freedom. They've been eaten by 2 vectors, and the lower component of the doublet, it has 1 more degrees of freedom, which has been eaten by another vector. So what does it mean? So upper component has a +1 dark charge, and there are 2 of them, and this means that they've been eaten by 2 dark matter candidates, and I'm coming to this. They're actually at the bottom. Well, the psi this is the vector-like fermion doublet. The upper component of vector-like fermion has a dark charge +1, while the lower component of the doublet has a 0 dark charge, which means that only lower component of the doublet can actually can mix and talk to standard model, while the upper component of the doublet cannot mix with any standard model particle. And finally, the vector triplet. We have V plus, V prime, and V minus, with respect of dark charge. And the dark charge is eventually +1, 0, and -1. So question is, what are dark matter candidates? And the answer is there are V plus and V minus, which carry the dark charge, but their electromagnetic charge is 0, of course, can be dark matter candidate. V prime is not dark matter candidate because it does not carry dark charge. It is not necessarily stable, so it can decay. Moreover, because it has zero dark charge, the quantum numbers are the same as the quantum numbers for the standard model photons or Z bosons. It's neutral and it's vector. So, well, with this term, we establish the connection to standard model, and the connection is done via this fermionic portal, and only this fermion actually mixes with standard model. Now I'd like to just write the Lagrangian for this model. So just writing the same Yukawa coupling, but with the more components. In principle, there could be several species. Well, not only one doublet, but several doublets. So that's why, in principle, Y prime can have a matrix structure. So it's not necessarily just one doublet. It could be several doublets, several generations. Well, and of course the model, I mean, you cannot avoid the Higgs portal. Higgs portal is still there, but you can easily put this coupling to be 0 at real level. This is the Higgs portal coupling, and still, arrange the thermalization of dark matter with the standard model particle via this term. Good. And finally, this is important thing. I just want to kind of jump here back. The electromagnetic charge of these fermions, it's the same as electromagnetic charge of this portal fermion. So if I write this thing, so electromagnetic charge of this doublet is the same as electromagnetic charge of the standard model right-handed fermion with which this doublet is mixing. Yeah, just to make sure. Well, do you have any questions? I mean, because this is the principal point of this model. I mean, yeah, looks like no questions. Okay, fine. I just want to make sure that actually you're happy. Well, so I want to then to show some phenomenology. So, I mean, to show what kind of phenomenology is possible for this model. So the red lines in the Feynman diagrams are those for the particles which carry dark charge, and VD is the vector dark matter, and you can produce, of course, in the different channels. And since Higgs, this is the dark Higgs or standard model Higgs. Well, depending on the mixing and the portal, but you can produce it via interaction. Well, you can produce pair of dark matter via Higgs. Well, there's a different channel when you can produce the odd fermions. Let's choose some model for concreteness. Let's choose the model where this psi is represented by the top quark partners. And therefore, well, in this doublet, there will be top D and top. This is the partners, vector-like partners of the standard model top. And in this case, you can produce, say, odd partners of the top quark, which will decay to top and dark matter, leading to the two dark matters and TT bar. which is TT bar plus missing. And there are also other diagrams possible for that. There could be diagrams even with the 4 top quark in the final state, or even more. I will mention about this later. Okay, this is fine. There could be interesting processes when you produce Higgs together with the V prime via loop, but this cross section will be not necessarily negligible. Could be sizable, or pair of V prime, V prime, V prime here, just to make sure. Well, it's this guy, which is not stable. The stable is V plus and V minus because they carry, this is lightest particle which they carry dark charge, but V prime will not necessarily be stable. Just want to kind of make sure that, so V prime will decay in this case to TT bar, for example, and so this process will follow, I mean, different, well, V prime decays. Well, if we choose the partner of standard model fermion, say, to be muon, so this is heavy muon doublet, M tilde M prime, so there will be partner of muon. Then there will be similar, well, the Lagrangian will be very, very similar, identical, but on the other hand, you can try to explain dark matter relic density and Z-2 anomaly if you still believe to the anomalous magnetic moment of the muon thing. And I still, well, personally, I take it seriously, though it's complete mess on the experimental side, actually, there. But it's not the subject of my talk. I will briefly comment on that. And so one has potential to explain dark matter is and Z-2. And I would like to mention what kind of parameter space we are talking. Okay, the model parameter space is described by, in general, 5 coupling. Well, you can, I mean, in our simple setup, we put the Higgs portal coupling to be small or negligible at 3 level. So it does not affect any Higgs properties. So the model survive with respect of Higgs properties. But it still has a 5 parameters. So one is the dark gauge coupling, mass of dark matter, MV, mass of the heavy Higgs, which can be actually, let's call me Higgs dark. It's new Higgs, new scalar. It can be lighter or heavier than standard model Higgs. This is the mass of the M prime. This is the even fermion or muon, partner of muon, and mass of the odd muon. But these guys must be quite heavy because they are charged. They carry the same charge as muon. That's why any new particles should be roughly, should be heavier than, say, several hundred GeV. To be precise, I'll give you precise limits from collider point of view, but definitely the charged guys must be heavy. Well, and these are Feynman diagrams which involve odd particles shown in red and even particles shown in black. So this is different Feynman rules. And this plot below, this is the sketch below, shows how the standard model fermion, which is phi left, mixes with the psi right. So psi is the new fermion, and F is the standard model fermion. So FL mixes with F right with the Higgs, then F right mixes with the psi left through the dark Higgs wave. This is the dark Higgs insertion, and then there is a fermion. Well, since it's fermion, a vector-like fermion, so psi L and psi R just can be connected through the mass term, which is actually here. I didn't mention this, but there is a mass term here. This mass term. So this is mass term for vector-like fermion, which you allowed. Good. Now, well, with this setup, we can discuss phenomenology of this model. One of the starting point of phenomenology actually would be understanding the mass correction to the dark matter and V prime. And it happens because of different corrections to the mass at loop level. V tilde, or mass of dark matter, is different from V prime, and it happens that V prime is actually lighter than V tilde. And the mass split is defined by radiative corrections. And this is the formula which is which gives this. So the mass difference between M prime and M tilde is related to the size of the Yukawa coupling. So for Y prime equal to 0, this means no portal. These masses, this difference in masses is 0, and there is no mass split between dark matter and V prime. So all particles in the triplet have the same mass. That's how it works. Now I will not. I tend to skip the discussion of the status of G minus 2. Well, I just want to say that if you believe to some experimental results, outside of very recent CMD3 results. So if you don't take into account CMD3 results, and take into account all the experimental results, there will be more than 5.1 sigma. If you take into account just the G minus 2 measurement combined at FNAL and BNL. Well, the CMD3 recent results, make some perturbation, and it's actually create some controversy. I'm not discussing this. I'm just assuming. Let's assume that there's some discrepancy between experimental measurement and the model theory prediction, which was existing in actually before CMD3. And I'm trying to explain G minus 2 also besides dark matter. However, if you don't want, if you believe that there is no G minus discrepancy in G minus 2, all results I will be presenting also will be valid. So it's up to you how to take G minus 2. And the contribution to G minus 2 in this model will be given, the contribution to G minus 2 comes from dark matter particles in the loop and V prime and Higgs, as well as together with the new fermions M prime or M tilde. So there's combined effect. So, and I wanted to show roughly how the contribution to G minus 2 scales. So first of all, there is a dark coupling squared, and there is an MVD in the denominator, and mass of the standard model muon, of course, here squared. But besides this, there is there are terms with a kind of similar contribution, but just want to say that one of the leading contribution will be, for example, from this diagram. This is mass of dark. This is the dark matter in the loop and M tilde in the loop. So that's why, if you would like to try to find a large contribution to G minus 2, while M tilde mass is limited and actually pushed to be heavier than, say, 800 GeV, as we will learn. The mass of dark matter is pushed to be actually quite low, because there is no magic, and mass of dark matter is the denominator here, and there's also mass split. Delta M is the mass split between M prime and M tilde, which is related to Yukawa coupling or Yukawa portal. Okay, so it's also controlled by Yukawa interactions. Now, this plot show how actually which region can explain the delta mu. So the delta mu 0 means that you actually explaining the deviation of in anomalous magnetic moment of muon using this model, and you explaining this difference. So delta A mu is the difference between observed discrepancy delta A mu and delta A mu predicted by the model. So this delta A mu hat is when it's 0 means that we have a perfect explanation of this deviation. And indeed, you can see, well, very naive plot when saying that the bigger mass of dark matter, the bigger coupling required to explain this effect, and we can explain this difference. This is the plot shows which shows how the delta A mu from new physics is related to mass of dark matter, and it's clear the smaller mass of dark matter. So if we go to the left, the bigger contribution, which it's exactly related to this formula. It's very simple, very obvious formula, and very quite obvious dependence. Now, roughly speaking, delta mu can be explained with this model we call mu FPVDM. This is the muon fermion portal vector dark matter model, when we choose specific fermion, vector-like fermion, to be partner of muon. So with the GD over MVD of the order of 0.1, that's yeah. So for for mass of M prime bigger than 1 TeV, it's hard by possible to explain this but it requires very light dark matter, as we see. And in order to explain relic density and direct detection experiments, non-observation in direct detection experiments and indirect detection experiments, well, we need to use tools, and these tools are basically, well, LANHEP, which allows to implement this model, CalHEP, which allows to calculate observables, and Micromegas, which link to the CalHEP. Micromegas, of course, is the package which use CalHEP as a core engine and has, of course, a very elaborated dark matter interface to that, which calculates and evaluates dark matter observables. And of course, for collider searches, we use CalHEP and MCET and NLO, Peter, Delphis. And in general, we use Checkmate as the chain of Peter, well, CalHEP, Peter, and Delphis. That's what we use for that. One more important message. In this model, there is no three-level interaction of dark matter and standard model quarks, light quarks, let me put this way. However, the interaction happens at at loop level. So V prime mixes with the photon and Z through the loops of M tilde and M prime. This is the kinetic mixing, but kinetic mixing at one loop level. And through the triangle diagram, again, V tilde can interact with the photon and Z via M tilde and M prime loop. This is a very important thing because this allows us to actually understand how it can be, how direct detection can constrain this model. And direct detection, the current status of direct detection is this. So I took, actually, there is a very nice reference and site where you can see the current limits for direct detection models. It's super CDMS / standard edu, and you follow this link, and you can click and open it right now if you like. You have PDF file, and it gives us the latest limits from direct detection, and we use this latest limit. And in fact, they incorporate it in Micromegas, but for yourself, just to understand what it is, I mean, you can get it from this site. So the strongest limit actually comes from, I believe, the LZ is already in operation and looks like it's has the best limits so far. But it's very similar to xenon and tone, which also well in operation. But anyways, we're reaching now, and the lowest point is below 10 to the minus 11 picobar proton scattering on the dark matter scattering on the proton. This is quite impressive. Quite close to the floor, but not there yet. Now, this is the first results for this model, and the plot is busy. I just want to kind of show few things. So the vertical line is the gauge coupling. The horizontal axis, so the vertical axis is gauge coupling, dark gauge coupling, and the horizontal axis is the mass of dark matter. You can see that the relic density, which is, I mean, the allowed region are shown in green and blue, and under abundant region is gray. So the green and blue are good, and you can see that genetic pattern is here. So the bigger mass, the bigger coupling is required, and this is the bulk annihilation region. Well, and this is here. So the Higgs resonant region, also shown here, it allows a slightly different slope and actually smaller coupling here in this region. A very important region is exclusion region by CMB. This is the orange one or yellow one. This is when dark matter is light, below 10 GeV, and you're simply killed by CMB constraints, because during CMB time, dark matter can annihilate to standard model particles, and this density, well, intensity of this annihilation is proportional, inversely proportional to mass of dark matter. So the lighter dark matter, the higher density of dark matter particles, and intensity of annihilation actually is proportional to the number relic density squared. So therefore, starting from 10 GeV, it's quite a killer. So, and realistically, well, this is light green region survives here for very light dark matter. I will explain why, I mean, later. I'm very close to my time limit. I just want to quickly browse what I wanted to show. So besides the green and light green region, there is a co-annihilation region, which allows, again, coupling to be very small. There is a dark matter co-annihilation with the dark muon, and this is this diagram. And of course, direct detection plays an important role, and it kills everything. Say, well, the purple region is excluded by dark matter direct detection. So these diagrams, essentially, these two diagrams, representative diagrams for that. Well, let me, yes, maybe if you ask me why this blue starts from this, but we just wanted to respect the lab constraints for which the charge vector should be heavier than 100 GeV. And yeah, I just want to go further. And this is the different projection. So in MHD MVD plane, it's clear that Higgs resonant, how the Higgs resonant well region behaves. So this is narrow band for the MHD MVD in the MHD MVD plane. And yeah, okay. Yes, I don't want. I mean, I would like to skip this discussion of this slide, but again, it's a different projections of the complete 5-dimensional scan. So it's like a millions and millions points there. So eventually, there are quite a few points survived, and this is good. But we did not apply a delta E mu constraints requirement yet. So now we're applying this. So what we want, we'd like to explain G-2 discrepancies at 2 sigma level. So, and this leads us to the purple region, which actually describes G-2. And you can see that actually the dark matter mass, which is horizontal axis represented by horizontal axis, is already limited to be quite low. And again, the reason for this, because um, M prime and M tilde are required to be large, heavy enough, then dark matter required to be light enough. And relic density, essentially, this region is realized only in the Higgs resonant region, which allows to avoid CMB constraints. I don't want to go into details. If you ask me why, I'm happy to explain this because I kind of have a limited time. But the region which survives is, well, for G minus 2, so you would like to have a light dark matter mass and low enough relic density, is lies in the dark matter annihilation through the Higgs resonance, which means that the new Higgs, the dark Higgs, is actually also should be very light here. Collider constraints. When one of the leading process for collider constraints, when you produce M tilde, well, the heavy fermions, which decays to dark matter in 2 muons, and collider constraints kills further relic density. So they require actually mass for for M minus or M plus M tilde to be heavier, to be larger than roughly 800 GeV. And if you require them to be heavier than 800 GeV, then dark matter is required to be lighter than something. And this lighter than something actually happens to be below 0.5 GeV. So the red region now is the final region, which explains relic density, satisfies collider constraints, and explains G minus 2. That's kind of final thing. One thing I wanted to kind of highlight, this is an exciting feature of these models. One of them is the following. You can produce 10 leptons or 10 muons for this particular model, 10 fermions in the final state. This is just a sketch of the diagram. So you produce, so not a sketch, it's one of the representative diagrams. So you produce M minus, M plus, the capital M's, which are even partners of muon. So they decay, well, each of them decay to muon and HD. HD decays to V prime, 2 V primes, and each V prime decays to 2 muons, mu plus, mu minus. So from each leg, you can have possibly 5 muons. So 5 plus 5 will give you 10. So it's quite impressive signature, and it's not suppressed because the cross section is controlled by 2-to-2 process, and the branching of each kind of branch, the branching ratio of Higgs d to V prime is of the order of 1, say 0.4, 0.5, 0.3, so still of the order of 1. Now, you can produce less than 10, you can produce 8, 6, and 4. This is example that you can produce 6 muons in the final state plus missing, when HD decays not to V prime, but to dark matter. And then you cutting out 4 muons. So instead of 10 muons, you will have 6 muons in the final state. But in general, you can have 10, 8, 6, and up to 2 muons plus met. And we did not explore this, and this is the, well, kind of, we preview this analysis. We're trying to actually do this analysis in the near future. And I will skip this table. This table, well, you can take a look later look at this table and characteristic for representative points and the cross sections for these 10 muons final state. I just want to kind of skip this. Very final thing. This model predicts sub GV V prime, which looks like dark photons, but not quite. Why? Because all known models with the dark photons, and which has been explored, these models described by only 2 parameters: epsilon, which is kinetic mixing, and mass of the dark photon, nothing else. And this is the kind of excluded parameter space from Na62. If you ask about this region from Na62, it's because the detector is actually placed at about 150 or 180 meters from the interaction points. So the dark matter should be living, sorry, the dark photon should be living long enough to reach this. But if it's living too long, too long, you will not observe it will be here. Or too short, you'll also miss it. So that's why that explains this shape. But it's not my point. My point is that in our model, we have one more parameter. It's not only kinetic mixing. So you produce photon, which have a induced kinetic mixing at one loop. We have this epsilon. But besides this dark photon we call V prime, which is not a dark matter because we have, again, just repeating, the V prime is the guy with the zero dark charge, which mixes with the photon in Z. But it has its own coupling to mu plus mu minus. And this is independent parameter. So we have one more parameter, which, and if this coupling is large enough, you can avoid all these constraints. So you need to consider actually three-dimensional space and make a picture in three-dimensional space instead of two-dimensional space. So this picture is too simplistic for dark photon in general. And this is our model is the actually more generic dark photon picture where you should consider three-dimensional space, including the coupling of V prime to mu plus mu minus. Well, now I'm just flashing. I'm not going to spend any minute on this. I mean, there's also very neat possibility from gravitational waves from dark sector, and we're exploring it. There's a team of people. And I'm proud to be among them because I'm learning a lot about the gravitational waves. So the dark sector and breaking of dark symmetry could be related to the strong first order transition, SFOPT, and it leads to the gravitational could lead to observable gravitational wave signal. And this is just a color map and this is the LISA result, which we show that there are some points which can be even observed by LISA. This is the red curve, which is quite impressive. But I'm not going to talk more about that. I mean, just prospects that there are very interesting prospects even from gravitational waves point of view. And I'm skipping this. So I'm going to summary now. So, well, the Fermion portal vector dark matter, what we call the FPVDM, is very promising. It's the whole framework. And the models, by the way, available at HepMDB. This is high energy physics model database, which we keep at Southampton. And it became official database for micromegas. And also it got a status of a permanent server at Southampton, which is a great thing. So it's permanent. And now this model incorporates many interesting possibilities for collider searches, cosmological implications, etc. And it has potential not only explain dark matter but also explain different things, including flavor, G-2, and even neutrino mass, which I didn't kind of discuss this, but there is also connection to neutrino mass. What else? I mentioned about flavor anomalies and in G-2. It has also prediction of multi-fermion signatures or multi-lepton if you choose lepton partner. But in general, you can have 10 standard model fermions and it's new smoking gun signature. Well, and it has non-standard dark photon, which is, I would say, generalized dark photon, which escapes present constraints. And finally, I just want to say that, the model also can, or not can, it exhibits a strong first order phase transition, which could lead to the quite exciting gravitational wave signal. Well, that's it for now, and thank you very much.
Thank you very much, Alexander, for the very nice and very complete seminar. Question from the audience? Any questions? Shisha had a question in the in the Feynman diagram that you show for the 10 final muon state and the other for the 6 muon state. Which of these two diagrams will have the largest ratio between signal and background, which will be more promising to be for
Well,
testing the model that you see?
Yeah, that's a good point. I didn't mention this. The background is 0. For 10 the background is 0. The background makes sense, and that's what we studied for this one. This is only 2 leptons plus missing, and the background is important to consider, and it's done. We did this analysis, and it's done here. But what's interesting, well, the background for, say, 6, 8, and 10 leptons is essentially 0. As soon as you observe few leptons, for example, for 300 inverse femtobarn, for these benchmarks, the number of events we predict is 2. This means definitely will be discovered, but we don't have 300 yet. And for 10 muons, we have 0.3 events. For 8 muons, we have around 1. And for this benchmark, so we need more luminosity. But once you observe 1, 2 events, it will be discovery. I mean, that's the thing, because the background is 0.
I had another question for the. Can you please provide a bit more comments regarding the potential of the model to explain these flavor anomalies?
Okay, that's a very good question. That's a very good point. So let me just go back to quickly to the Lagrangian, initial Lagrangian. Okay, this model, okay, let me just, sorry, I was too fast. Yes, this is the Lagrangian, and this is Yukawa interaction in general, right? So you can see that there's the Yukawa term, which interacts with the vector-like fermion, psi, and you can include several generations here, and you can include several generations of fermion, standard model fermion, right? So you can have some texture and flavor pattern in using this Yukawa matrix, and you can explain the flavor anomaly. Well, unfortunately, LHCb looks like, well, anomaly excitement became much less appealing, but still maybe somebody was interested in this. But using this Yukawa and including 3rd and 2nd generation of fermions would allow us to explain flavor anomaly at LHCb, for example. That's the, well, we didn't do this, but it's back on the envelope. After some discussions, it was clear that there is a potential of this class of models. It's not a model, it's kind of class of models, depending on how many fermions you include and what you do. So, and this class of models has potential to explain a flavor anomaly using the texture pattern of the Yukawa. That's kind of thing, involving different flavors of this psi and standard model right-handed fermions.
Thank you, Sasha. More questions from the audience?
Yes, I have a question.
Yes, Claudio, come.
Hi, Sasha. Good to see
Hi.
you.
No, thank you. Yeah, same here. Yeah.
Can you go back to this slide 33, where you showed the, the QB bar going to 10 muons?
Yes.
So I was wondering, well, first of all, is this 10 muon signal Is this a dominant channel here, or is a highly suppressed channel, or what is it?
Okay, good. Okay, so let me put this way. So the current limit on the muon, well, discharge partners of muon is 800 GeV, and of course, if you produce these guys with 800 GeV without any further decay, I mean, it would be at the moment the strongest limit looks like comes from this. However, if you have slightly higher luminosity, this channel would become the leading one, because I would say, okay, the branching at each point, the branching is of the order of, say, 0.3, 0.4. I can show you a table. So the branching, for example, HD, here it's 0.6, 0.3. So it's of the order of 1. This means that at each branch, it's of the order of 1. But look, there are quite a few branches, right? There is a vertex here, vertex here, vertex here, vertex here. So it's already 1, 2, 3, 4. And even 0.5 to the power of 4 will give you suppression by factor of whatever, 10, right? So this is kind of dramatic. So therefore, if you consider all these kind of branchings, it's a factor of 100 of suppression, right? So therefore, I mean, without this decay, this would be for sure the dominant process. But realistically, since each vertex has a suppression of, say, factor of the order of 0.5, well, this would be maybe not the leading discovery signature, but if one can, I mean, we didn't explore the whole parameter space, and the answer is that it could be the leading one for certain points in the parameter space, and with the 300 inverse pentabarn, you see already kind of pattern. So in principle, you can have several events at a higher luminosity, and even one event will be discovery. So just to make it short, this multi-lepton signature could be the leading one. Maybe not 10, maybe 8, but I just want to keep less number of splitting. But we did not explore this fully, and but it has a very exciting and promising prospects. That's what I would like. We didn't explore this. I just draw this as it's my recent drawing. I realized that it's very exciting and it must be explored. It could be the leading one.
Yes. And now the question is, are those all those decays, very short range? So the M prime, etc., they decay almost instantly. So you can say
it's prompt. They're prompt. They're not long-lived. No, they're prompt. Except maybe, well, it depends. V prime. No, that's it's kind of. No, they're all quite prompt. Yeah, I can show you. Yeah, actually, it's a good question. It's an excellent question.
Because all the muons come from one point, and not you have displaced vertices.
We checked this, and actually, it's not shown here. But in the paper which is coming, yeah, the lifetime is not short and not long enough to see the displaced vertices for them. No.
Very good.
Yeah. Okay, Alfonso.
Yes, hello, Sasha. I have a question, a very nice one, as always. In the formulation of the model, you choose SU2 as the group of the dark sector. Could this group be enlarged to consider a larger group, or would be any advantage consider a larger group?
Well,
in order to have a more dark particles.
Yes, actually, that's a very interesting question, and this must be explored. Well, I think that, let me just go, well, for example, this one. If you go and consider, say, SU3, for example, right? So dark SU3. Well, then there will be more charged particles eventually, and then we need to have we need to have a larger scalar sector, right, to break it, because we must break it, right? So, and
Yes.
it could be, I would say it would be non-minimal, but it could have a qualitative difference because you could have probably even multi-component dark matter. I don't know. I mean, uh, well, for sure, this is minimal thing. Well, but maybe it's worth to explore the SU3 because it could lead to if you have a triplet. No, it's interesting because I'm thinking about, so Yukawa interactions would stay the same, right?
Yes.
Identical. Well, but dark matter itself will be different, completely different. It's like well, 8 gluons, right? So we can have like,
Exactly. Yes.
yeah. In this case, there will be more dark, and probably it will be only one. Uh, uh, one. I need to think about the charges, right? So, well, I, I, I don't want to lie to you, but it's. I think it's worth to explore this. One can think about this. I didn't think about this yet. I was so excited about this construction, minimal construction, which can explain everything, and plus many interesting things that I didn't even think about the SU3. But yes, it could be some qualitative difference, even in signatures and pattern of the missing ET signatures. Yeah, and relic density predictions and many things. Well, could be even qualitative difference. Yes.
Thank you.
One should explore next to minimal, well, vector dark matter then. That's what I would call it. Yeah.
Yeah.
More question from the audience? I would like to comment also that if one consider possible, for example, SU model with an SU3 DAR, it seems to me that the dark chair will be defined in a similar way as in the T31 model, like T3 plus beta TA plus X, where X will be in that case an extra, not only S3 DAR, but maybe DAR U1 X chair will be needed. And then in that case, depending on the choice of the beta parameter and the choice of the DAR U1X chair, I seen someone can have, for example, in the SU3 DAR scalar triplet and Fermionic triplet, one may have some two components, for example, to have to have dark char, non-vanishing char or non-vanishing char. So there could be, as I say, multi-component dark matter. So it seems will be interesting scenario.
Yeah, yes. I have a feeling it could be qualitatively different, not just increasing the size of the gauge group, but it could lead to the actual qualitative difference to the multi-component dark matter.
Yes.
That's
More
absolutely right.
questions? Yes. More question or comments? From there are more questions from the audience or comments? If there are no more questions, we thank Sasha for the excellent seminar, very complete seminar. Thank you so much, Sasha, for the very nice
Thank you for
complete seminar.
invitation. It was fun. I really enjoyed it, and maybe we should work together on the well, SU3 Dark, and this would
Yes,
be
yes, it's a nice project. Yes,
yeah.
we
Good.
should. Yes, yes, I'm collaborating on that project. Yes, to 3 it will be nice.
Thank you. Thank you very much. Well, was great. So, well, I hope to see you all guys in January. Well, in the beginning of January, right? So when you have this, well, I was invited to come to a place. That would be good.
Excellent. Yes.
Yeah.
We'll be very happy to have you here in January. Yes. We'll be very great that you will come. Thank you so much, Shasha.
All the best. Thank you. Thank
The
you.
best.
Claudio,
See
thanks.
you.
Yeah.
See you. Have a nice time, all of you.